So the condition part, I wrote it down myself in here. Condition part says Q and R are quotient and remainder, right? Not really, it didn't put anything about R. So this lemma is really saying anytime if you write A as a BQ plus R, no matter R is a small or negative, positive, doesn't matter. Whenever A is written in that form, the greatest common divisor of A and B is equal to greatest common divisor of a B and R, right? But if we use, what is it? The division algorithm, R becomes smaller. So you can look at the one problem with a larger number and you can switch to the smaller number problem, right? That's the advantage of this thing. Although statement is still true whether R is a small number or not. So let's do this, get used to this one. So here's an exercise I want you to do. Exercise number 9, I think it's from the book. 343 and 280. So this is what we're calculating now. So I want you to write them down. And you see, if you look at this lemma, the B and B is right next to each other. I think that's a really easy thing to remember. So that's how I do this algorithm quickly. So B and B is right next to each other. I will write 280 right there. Is that all right? B and B are right next to each other. Is it kind of similar to what you see in the lemma? Good? All right. Then what is this R? If you're looking at A and B, which is two number, and we're computing the greatest common divisor, and it's the same as you start with the B, the second number becomes the first number, and this can be the remainder when you divide A by B. That's what this statement can be interpreted as. So I want you to go ahead and divide 343 by 280 and write down the remainder right here. That's what this one is suggesting, right? What was the quotient when you divided it? Only one copy of 280 goes into 343, right? And you subtract it, you have a remainder of 63. So I want you to record that quotient right there. Underneath it, write down Q was 1 there. Good? All right. Now you're looking at the same problem again. 280 and 63. Greatest common divisor of that one is our original problem. It's equal to our original problem, right? So let's do that one more time. What do we do? What is the first entry here to write down? Adjacent one. They're the same. The 63 goes there. And what is the second term? You divide the 280 by 63 and write those remainder down there. And somebody tell me what the quotient is. So we got quotient 4. Second person, get quotient 4. Quotient 4. Who wants to go for remainder? Somebody said remainder is 28. Check 28. Good. So you're already down to 63, 28 versus 343 and 280. But it is all connected by equal symbol, not by arrow. These are all same number. Miracle. Okay? So let's do the next step. What is the next step? What do you write that? Adjacent number 28, right? Yeah, somebody go for identify Q and R here. Ben said Q is 2, and Joseph said R is 7. All right. This is good. 28 and 7. Now we know. Let's do one more silly step here. So 7 is written down here, right? Because then what is the remainder here? The 0. And then here Q is 4, right? That's it. And what is the greatest common divisor here? 7 and 0? 7 is the largest thing that divides both of them. So the greatest common divisor of 343 and 280 is 7. What is this algorithm called? Some ancient guy? Euclidean algorithm. Don't you like this? Whenever you see this type of thing from Legendre and Gauss and Euclid, and you give them a big hand. Well, this is great. You don't have to factor anything. You just boom, 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 knock them down, and there's a greatest common divisor. So this is a good thing to remember. All right? Exercise that I want you to do this on your own, right? All the way to the end, just like doing this repeat. So here's the some exercise problem. I wrote it down. I think it's the same 9. So it's 578 down to 442. So I'm going to be doing that. I just copied down, I'm cheating here, copied down my answer. So you do it on your own. I'm going to stop recording and just write down my answer. But you're supposed to work on your own. So this is what I got. I got down to 34, and the sequence of quotient was q and equals 1 and 3 and 4. All right? Any question about this algorithm? It's a pretty cool algorithm. And proof, I mean, why is it true? It's relying on this lemma 3, and proof of this statement is shockingly simple. And we're going to, at some point, look at this proof. But that's there. That's how it's interesting and cool this algorithm is. What is more interesting for the rest of this whole course is this the fundamental lemma, which is in next page. I want you to look at page 8. Here's a theorem 4, right? Here's a number 4. So it basically says this. If you have number a and b and its greatest common divisor is d, you know how to calculate its greatest common divisor, right? How do you do that? Use your Euclidean algorithm. Then it's claiming not only the greatest common divisor you can calculate, but you can also write down this interesting statement. Ax plus by is going to be d, right? So if you have, think about it, if you have large number a and b, very large number, like 5-digit number, and it turns out they have no greatest common divisor, and it is telling you, that means greatest common divisor is 1. They're telling you there's a nice linear combination, this two large number as an integer and add up to become a 1. That's an interesting statement, and this is going to be the foundation of the many, many things into what's coming in the number theory. All right? So here is how you see this one. I'm going to show you an algorithmic approach to this problem. So I'm going to look at first example and exercise 9 there. I'm going to start with this one. I'm going to call A and B an example. This will probably convince you that, hey, that's a proof. I don't need any more of the proof. That example is a kind of proof to me. So I'm starting with A, 343, and B, 280. Early example, right? So I want to look at this one as a more vector form. I have A and B there. And next moment I have this 280 and 63. Those are the two numbers. It wasn't a vector before, right? Don't look at it as a really vector up there. It was a GCD symbol, right? But it is the information about two numbers, so I turn it into a column vector. And think about what matrix should I multiply here to get this 2 by 2 size 2 column. All right? How did I get this 280? 280 was B here, right? 280 was B. So what number should I put it here that nicely picks up that B? 0 and 1, who said that? Ben said it's 0 and 1. Does that work? 0 and 1. If you multiply that, it'll pick up 280. Think about how do we get the 63 down there. 63 came from some division algorithm. We divide 343 and so on, right? Good? So how do we get that? It was this statement. Where was this statement? Here's the A equals BQ plus R. That's how we got this 63 there, right? So can you write down 63 in terms of A and B so that you can put it into a matrix here? 1 minus Q. Is that all right? 1 minus Q. So what's Q here? It's 1 here. In this case, it's 1, so it's a 1 here. So you can see it's A minus BQ is R. That's how you write down 63. So if you separate this A and B from the matrix, it's a 1 and negative Q. Good? All right. So that's how you write down. So think about what happened to 280 and 63. And what is the next number we get? 63 and 28. Is that right? 283, 63 becomes 63 and 28. So we're going to figure out matrix again such that that takes 280, 63 to 63, 280. Same phenomenon. Bottom entry becomes the top entry, right? That's the phenomenon. So what do you think about the first row of the matrix? 0 and 1. That'll do the same business, right? And take care of it. What about the second, the bottom row? Right, how do we get this 2 and 28? That's the, 28 was the remainder, right? So before that was a 280 minus 63 times some quotient that was involved in the process, right? So if you separate 280 and 63 to that column vector, what's left in is 1 minus q again. So 1 is here. What was the q this time? Was a 4. Okay, involved this was a 4. So negative 4 there. 0, 1, and 1 is always the same. Is that right? 0 and 1. The q goes there. So here's this bit that I'm about to put them all together, and here it is. We start with AB, is that right? And first we multiply this matrix 0, 1, and 1 and negative 1 to get to this 280, 63, right? What do we do about the 263? We multiply one more matrix to the left, right? To the left, 0, 1, 1, negative 4. That thing is 280, 63. That bracketed part, 280, 63. Multiply by that new matrix. So what is that supposed to be? 63, 28. All right? You see the pattern? You start with AB. You keep multiplying the matrix to the left. And the shape of the matrix is fairly simple, right? So let's do that. The final picture. All right, go up there. What is the last one? Is that 2? 2 is the last one, right? Okay, so that I'm going to do 2. Here's A and B. And here's 0, 1, 1, negative 1. 0, 1, and 1, negative 4. And last bit was 2, right? 0, 1, and 1, negative 2. And that's supposed to be 28 and 7. And from that calculation, we know 7 is what? Greatest common divisor. You don't have to go down to 7, 0. You did that before. You know 7 is the greatest common divisor. So you calculate the left-hand side, right? And the bottom entry is 7. That's all what we have there. And you can see if you simplify this product of 3 matrices, multiply by AB, it'll be AX plus BY, right? So I want you to go ahead and simplify this matrix, product of 3 matrix, and write down AB here, and write down 28 and 7. Okay? Go ahead and calculate the product of that 3 matrix. All right, this is what I got. Negative 4, 5, and 9, and negative 11. Did you get that? Okay, so you go ahead and write them down. All right, I simplify the matrix, negative 4 and 9 and negative 11. Is that right? All right. What was interesting number though? Well, where's the GCD? GCD is right there, 7, right? Smallest number we reach. So we only care about the bottom row here, right? So we don't have to multiply. So we multiply A times 9, 9 times A, minus 11 times B is supposed to be what? 7. That's the bottom row there. So what was A? A was 343. So here, 343 times 9, that's your X right there. That's your X. Plus, what was B? 280. So 280 times what? Negative 11. That's your Y. And becomes what number? GCD of 343 and 280. Okay? And it is a theorem. You cannot go below GCD except 0. This is the smallest number you will ever reach by playing with this 343 and 280. However you add and subtract, as long as this x and y are integers, this is the smallest positive number you will ever reach. And this is important result. How do you reach that? There is a secret number, 9 and negative 11. Right? When you do the congruence calculation, this becomes a fundamental tool. Without this one, you can't calculate anything in the modular congruence. It's a very, very important statement. Unfortunately, this theorem does not have a name. My advisor, my, number theorists I admire, they never call this any theorem, it's number. But I think is very, very important. So I'm going to name it, right? Fundamental theorem of a linear Diophantine equation. If you next sections are linear Diophantine equation, and it is a fundamental result there. So I'm going to call fundamental theorem of linear Diophantine equation, right? You like that algorithm? Do you think that's a proof? Do you think that's a proof that proves to theorem 4? I want you to stare at the theorem 4. I mean, it's not a proof, but does that give you sufficient idea to prove this thing? Right? If you believe the matrix business is true, because each time it takes that, it's going to be difficult to write down the neat proof of this, right? Because we understood the process, but writing it down is fairly tricky proof. So there's a different proof, elegant proof. It does not deal with this algorithm at all. It just shows that it reaches D, not telling you how you calculate x and y, just the existence of x and y. There is a better elegant proof. But this is more informative. It has more information in it, right? All right. So let's go back and think about even more important theorem, lemma 3, right? Lemma 3, I'm attacking this one verbally. And since book has a proof, and I want you to attempt your own proof, let's go and think about it this way. This is what we want to prove, and let's look at the statement one more time. A equals BQ plus R, right? All right? Then we have clearly notion of A and B, the greatest common divisor. I'm going to call that one D. Okay? And there is a two different number, and B is a common, and B and R is the greatest common divisor. I'm going to call E. And you want to show, rather, suppose this is given and we're calculating this greatest common divisor of B and R. Why is that D? That's what we have to show. This is claiming the greatest common divisor of the GCD of B and R is D, right? So maybe I'm going to put why is that D? That's better. Okay, that GCD of A and B is called D, and you think about why is GCD of B and R is D. That's what you have to prove. So let's think about the first thing we did. What is the first thing we did in this class? You wrote down something. What is GCD? How do you define it, right? Two things, remember? So here is, we're showing that GCD of this one is D. That's what we want to show, right? So what is the first thing? To show D divides B and D divides R. So why is that? Somebody explain, why does D divides B and R? This part is easy, I think. Why does D divide B? D is the greatest common divisor of A and B, so that's given. Is that what you're saying, Jose? Good. What about R part? This is the tricky part. You have to use this equation, right? D divides A, D divides B, therefore D divides R. Why is it therefore? Have you seen any lemma like this? We've done that in earlier chapter. A lot of lemmas are, if two terms are divisible, sum and difference are divisible by the same number. Things like that. That make sense? It has a factor of D. It has a factor of D there. Therefore, we must have a factor of D, this remaining term. So D divides R is clear? Right? So what is the next thing you have to show? Anything that C, right, divides B, and anything that divides which one? we're calculating this one here, right? So anything that divides B or anything that divides R, and then what is the conclusion? Less than or equal to D. That's what you have to show. So we have this number C, which is dividing B, which is dividing R. That's given, right? How do you conclude C is less than D? D is about A and B, and C is about B and R. How do we connect them to that? C divides B and C divides R. C divides B and C divides R. C divides what then? C divides A. So C divides A is from there. We also bonus, we have C divides what? A as well, right? Then what's the next part? C divides A and C divides B. That's a common divisor of A and B. Why C is less than D? Because D is the greatest common divisor of A and B, and then we show that C is a common divisor of A and B. Therefore less than that. Right? That's how the proof goes. Does that make sense? Yeah. So that's how the proof goes, and it has powerful consequences. Right? You just saw that in the last 20 minutes or so. Powerful consequence of this simple divisibility around there captures the GCD. Not only that GCD, more important theorem. What was that? Fundamental theorem of what? Linear Diophantine equation. That's the important part. All right? All right, do your best.